Center of mass is kind of, you can think of it like the average position of the mass of an object. So for example, for a real uniform type object, like maybe this pen, the center of mass is going to tend to be right in the middle. You've got some stuff over here, you've got some stuff over here. The average position of the mass is somewhere in the middle. And in fact, it ends up being the balancing point. I'll show you why in a minute. For an irregular system like a hammer here, you've got more mass over here, less mass over here, so the center of mass is going to tend to be over in this direction. You can imagine if this was a million pounds and this was or a million kilograms and this was 0.1 kilograms, the center of mass would be almost right here. As it is, it's probably, let's just say 1 kilogram head. It's not, but and 0.2 kilograms for this. Once again, this is kind of uniform, so the center of mass of this part would be here. So 0.2 kilograms here and 1 kilogram here. You can tell the center of mass is going to be closer to there. And it actually works out just like torque. If we think of 1 kilogram being right here and the mg is 10 newtons, and if we think of 0.2 kilograms right here and the mg is 2 newtons, well, there's going to be a spot right here, somewhere over here, where the torque, Rf, equals this torque. So that's why it balances. So if I figure out where it balances, that's where the center of mass is. And you can see it's way over towards the heavy part. And in fact, any kind of system, any kind of object, it's going to end up being that balancing point. Here's why. If you have a normal force, I had my finger here. It was providing a normal force. If the center of mass goes right through the normal force, it's not going to tip. If the center of mass was over here, then the mg of the entire system would have a torque around my finger, and it would make it rotate that way. So when my finger is to the left of the center of mass is here, provides a torque, and it rotates. The center of mass follows all the rules that we learned before. If you look at a tennis racket, the center of mass is near the bottom of the head there. And so when I throw it, it's going to follow projectile motion. All the other parts are going to rotate around that point. High jumpers are kind of interesting because their center of mass actually passes below the bar. They don't actually put their center of mass over the bar. You can see most of their body is under it at any given point. Ruler has a center of mass right in the middle. So when that center of mass, or mg, moves past the edge of the table, there's a torque and it falls. How could I make that balance but stick out farther? I got an idea. Maybe I'll stick some more mass on the end of that. That'll help it balance, right? What? Why does that happen? Here's why. Because the center of mass of the system is now under the base of support. It's right where my finger is. So it doesn't torque. Why doesn't this bike at a science museum fall over? Well, because that thing at the bottom has a lot of mass. So the center of mass of the system is below the tightrope, so it's stable. So complex systems will balance if the center of mass is under the point of suspension. Now I got a fork and a spoon and a toothpick, and after a whole lot of fussing, I was able to get it to balance. And what you can see is the center of mass of the system is below the lip of the mason jar and right under the point where the toothpick is resting. So it looks like, oh, well, maybe that's part of the toothpick has something to do with the balancing. Not really. It just provides the structure. So the center of mass is under the lip of that thing. Even if I burn away all that part of the toothpick, it still balances. Now, if the center of mass is above the normal force, you have a different situation. It's not as stable. Here's why. Because here's my center of mass, here's my base of support, right? Right now, I've got the normal force coming up here, center of mass here, there's no torque. But if I'm a little outside my base, there's a torque, and I fall over, I rotate. So that's the thing called stability. If you have a really, really narrow base, your center of mass, it's harder to keep your center of mass over it. If you have a wider base, look, you actually have to raise up my center of mass to get me to go over, and that's called toppling. So they sometimes talk about lowering your center of mass, but really it's just as effective to widen your stance, to widen your base, because it makes it harder to move the center of mass up and over the end, because that's called toppling. The base doesn't even have to be that wide. Here we've got a beaker. Can't bounce a beaker on the corner because there's no base really. It's a little tiny, tiny base. But if I take salt, I can, after a little bit of trial and error, get it to balance, because now there's a base. The center of mass actually has to move a little bit. What's amazing to me is I can blow away almost all the salt that's not supporting it. And it's still enough of a base. It's just a few grains wide, as you're going to see in a second. Just a few grains of salt holding this up. That's enough of a base. The center of mass is between the sides of the crystals of salt that are holding it up. There it is, just a tiny little piece. You might have seen this demo before, but girls' centers of mass are lower in their body. So even when she picks up this chair, the center of mass of the system is somewhere over her balls of her feet. So she can just stand up and do that. Guys, it's a little different. We have higher center of mass. And when we pull that chair up and lift that up, the center of mass is really close to the tips of our toes, maybe a little outside. It's so hard.